Welcome back to video number 3. We've been mostly just going through terminology of differential equations. We started with the existence and uniqueness theorem, and then we went to the definition of a boundary value problem or an initial value problem. And we ended with another theorem that says that if you have multiple solutions to the homogeneous differential equation, that you can add those two solutions together or more. You can add them together, and what you'll end up with is another solution to the homogeneous differential equation. So I'm going to define a couple terms. I'm going to start with a set of functions is linearly dependent if there exists some sequence of constants not equal to 0 such that C1 F1 plus C2 F2 plus all the way out is equal to 0. And if this condition fails, then we have a set of functions which are not linearly dependent, is said to be linearly independent. What this means is what we're aiming for. If I'm saying the two functions are linearly dependent, that means that you can get one of the functions through some combination of the other functions. And if they're linearly independent, that means that you can't get one function, any of the functions, from a combination of the other functions. For example, just ignoring the sort of infinite number of functions that are possible here, we can just talk about two functions. For example, x and x squared are linearly independent because there's no constant I can multiply this by to get this. There's no constant I can multiply x squared by to get x. So we say that they're linearly independent. And going forward, I'm just going to abbreviate that as Li. Another example of linearly independent functions are cosine x and sine x. There's no number that I can multiply sine x by to get cosine x, and there's no number I can multiply cosine by to get sine. So these are linearly independent. We can contrast this with something like 2x and 3x. These are two different functions, but I can multiply 3x by 2/3, a constant, to get this function. Thus, these two are linearly dependent, and I'm going to abbreviate that as LD. Or sometimes Linda. Going back to our definitions, This initially will seem unconnected, but we will quickly see how it's connected to the concept of linear dependence and linear independence. The determinant we'll call it W, which is the determinant of F1, F2, all the way out to Fn, F1 prime, F2 prime, all the way out to Fn prime, all the way down to F1, the nth minus n minus 1th derivative of F1, the n minus 1 derivative of F2, all the way out to the n minus 1 derivative of Fn. This is called the Wronskian. And we notice the dimensionality of W. We're always going to take the determinant, but the matrix itself has dimensionality of n by n. It's a square matrix, which is good because that's a requirement for a determinant. But we're always going to end up with a scalar here. So, for example, if we construct the Wronskian or calculate the Wronskian for some of the functions that I just showed you, the Wronskian of x and x squared, this is x squared, and then the derivative of x is 1, the derivative of x squared is 2x. And when I multiply these together, I get 2x squared minus x squared, which is just x squared. I can calculate the Wronskian of cosine x, sine x. This is cosine x, sine x. The derivative of cosine is negative sine. The derivative of sine is cosine. And so I get cosine squared of x plus sine squared of x, which simplifies to 1. That's cool. And the Wronskian of 2x, 3x is 2x, 3x. The derivative of 2x is 2. The derivative of 3x is 3. And here I get 6x minus 6x, which is equal to 0 for all values of x. And what we notice here is the first two sets of functions that I gave us, x and s squared, or x and x squared, cosine x and sine x. Here we got x squared and 1, and on the set of functions that I said was linearly dependent, we get a Wronskian of 0. Well, this goes back to the definition of what it means to be linearly dependent. We remember at one point in time, we used matrices to solve systems of equations. Systems of equations are given variables. We're looking to find the values of those variables which make the equation true. So if I imagine this as a problem to solve, finding values of C1, C2, and so on, which make this statement true, we can see the connection to using matrices. And in fact, we know how to, using only matrices, solve a system of equations. So let's clarify the observation that we just made, and that is if fi of x is a set of functions with the Wronskian not equal to 0, then we can say that fi is linearly independent. So this gives us a quick and easy way to check to see if any set of functions is linearly independent or linearly dependent. We just calculate the Wronskian. And if that Wronskian is 0, then it's linearly dependent, else linearly independent. So let's do one more example. All of the examples so far have had 2 functions. So let's calculate the Wronskian of the family of functions e to the x, e to the 2x, e to the 3x. So we have the first row, e to the x, e to the 2x, e to the 3x. The second row is the derivative of that, e to the x, 2e to the 2x, 3e to the 3x. And the third row is e to the x, 4e to the 2x, 9e to the 3x. And here we have e to the x times 2 times 9 is 18. E to the 2x times e to the 3x is e to the 5x minus 4 times 3 is 12. E to the 5x minus e to the 2x times 9e to the 4x minus 3e to the 4x plus e to the 3x times 4e to the 3x minus 2e to the 3x. And what we end up with is 18 minus 12 is 6. I have 6. E to the 5x times e to the x is e to the 6x minus 9 minus 3 is 6. E to the 4x times e to the 2x is e to the 6x plus 4 minus 2 is 2. E to the 3x times e to the 3x is 2e to the 6x. And we end up with 2e to the 6x. Let's double check our work. We have e to the x times 18 minus 12. 9 times 2 is 18. 4 times 3 is 12. 18 minus 12. 18 minus 12 is indeed 6. And then I have e to the 5x times e to the x, so that checks out. Next up, we have e to the 2x. 9e to the 4x minus 3e to the 4x is 6e, and then to the 6x, and then e to the 3x. 4e to the 3x minus 2e to the 3x, 4 minus 2 is 2. E to the 6x, so we get 2e to the 6x. So here we get that this Wronskian is not equal to 0, and so this set of functions, e to the x, e to the 2x, and e to the 3x, are linearly independent. Going further, we've verified they're linearly independent. Let's see if they solve the differential equation y, the third derivative of y minus 6 times the second derivative of y plus 11 times the derivative of y minus 6y equals 0. So we can check with each one of these, letting y1 be equal to e to the x. This gives us e to the x minus 6e to the x plus 11e to the x minus 6e to the x is equal to, I can factor the e to the x out, giving us 1 minus 6 is -5. -5 plus 11 is 6, minus 6 is 0. So that solves the differential equation. Checking y2, e to the 2x. We have the third derivative. The first derivative is two e to the 2x. 2 times 11 is 22. The second derivative is 4e to the 2x. 4 times 6 is 12. Nope, that's not true. 4 times 6 is 24. And the third derivative, let's see, we had 2e to the 2x, 4e to the 2x, 8e to the 2x. And so we can factor out the e to the 2x from everything, giving us 8 minus 24. 8 minus 24 is -16. Plus 22 is 6. Minus 6 is 0. So that solves this differential equation. Trying y3, e to the 3x. The third derivative is, let's see, we have 3e to the 3x, 9e to the 3x, 27 e to the 3x minus 6 times the second derivative. The first derivative was 3e to the 3x, so we have 9e to the 3x plus 11 times the first derivative. That's 3e to the 3x minus 6e to the 3x. Again, we can factor out an e to the 3x from everything. 27 minus 54 is -27. -27 plus 33 is 6, minus 6 is 0. And so what we have is, we have 3 linearly independent solutions to this differential equation, which according to our theorem the other day, since this is or from earlier today, since this is a homogeneous differential equation and each of these solve the homogeneous differential equation, we can construct another solution, which is C1 e to the x plus C2 e to the 2x plus C3 e to the 3x. All right, I'll see you in a couple minutes for the next video.